Welcome to the Shearwalls online tutorial videos. In this tutorial, we demonstrate how to model a single wall instead of an entire building, how to apply a seismic or wind force manually, and how to add supplementary loads such as wind uplift and vertical dead loads. Here is a simple building. When you want to design a single shear wall, we only really care about that particular wall geometry. So it is only a matter of drawing a single structure block, specifying the extents of the structure block, going to the wall input view, modifying the length of the wall, then going to the openings view and adding any openings. You can then return to the wall input view and specify desired wall details for your shear line. All of the walls in this structure are designed with the same materials and framing details, but we will only be focusing on shear line A1, which has an opening of 1.5 meter with a 3 meter offset from the edge, as you can see in this elevation view. Since we will only apply a load to one shear line, we will uncheck the feature to conduct a rigid analysis. This will prevent a warning expressing that the rigid analysis was not performed because not all shear lines were loaded once we run the design. Instead of generating automatic loads, let's open the Loads and Forces form view to manually add loads. The message that pops up is a reminder of the recommended steps to follow when adding manual loads. By clicking OK, you can see that when adding a new load, you have the choice of its type, profile, location, and magnitude. There is also a feature where you can add a factored force directly parallel to the shear line. Since we only want to demonstrate the effect of a load on a single shear line, which is wall line A1, we will check this feature and add a factored wind point load of 35 kN parallel to shear line A1. If I did not toggle this factored load option, I would have added an unfactored wind load, which, after running the design, would have been factored by 1.4 as per load case 4 from CSA 086 table 5.2.4.1. As soon as we run the design, a warning appears stating that undercapacity shear walls were found. By going to the design summary, we can quickly determine which wall fails the design. For this reason, this section is very practical, especially when multiple walls are involved in the design. Furthermore, by navigating to shear results, you can determine exactly what segment of the wall was designed under capacity. In this case, each wall segment fails to resist the wind shear point load, which generates the following warning in red. For more details on information generated in the result pages, refer to the series of videos Understanding the Results, going from 5.1 to 5.5. Now, we will redesign our wall with other materials so it has sufficient capacities to withstand the 35 kN factored wind load force. By adjusting the thickness of each ply of our Douglas fir plywood from 7.5 to 12.5 mm and rerunning the design, the ratios of the previously failed wall segments are now below 1.0. That being said, properties of the newly designed wall can resist the 35 kN factored wind force. When designing with shear walls, and when automatically generating loads, only horizontal wind loads are generated based on the walls, floors, and roof areas. In reality, vertical forces like wind uplift loads and dead load that resists overturning forces also exist, but these are not generated by the WoodWorks software, as the level of load is dependent on the orientation of the framing members. Since it is not currently possible to specify the orientation of the framing in shear walls, it is necessary to apply these loads manually, which I will demonstrate next. You can access and add those wind uplift loads manually by going to the Loads and Forces tab. Adding wind uplift loads and dead loads to resist overturning does not contribute to the lateral loads that the light frame wood shear walls will be designed for, but these forces do have an influence on the hold downs present in the structure. Let's see the effect on the hold downs without and with those added vertical forces. Let's rerun the wall we just looked at, but using a factored wind shear point load of 20 kN instead of the 35 kN. By going to the Wind Design Flexible Diaphragm Hold Down Design, you can see in the critical response column that the hold downs on the left and right segment of wall A1 are respectively solicited at 45% and 60% of their total capacity. We will now add a wind uplift load of 2.85 kN per meter to the same model. You would determine your uplift based on the code requirements and your local climatic data. For a Q1 in 50 pressure of 0.65 kPa, and based on a building width of 8 meters, the Canadian Wood Council's engineering guide has an helpful table that provides the factored uplift at the eave. Our value of 2.85, which the software will automatically factor by 1.4 when running the design, is about 4 kN per meter, similar to the table. By rerunning the design with this new wind uplift, we can see that the hold downs on the left and right opening, as well as the right end of the wall, now have a critical response above 1.0. Therefore, they are under capacity and higher capacity hold downs would be required. Now, let's take a look at the option to manually add dead loads. Similarly to wind uplift forces, dead loads are not accounted for in the design process conducted by the Shearwall software. Remember, we are talking about dead loads, which are used to help reduce uplift of hold downs and not building mass. The difference is described in another video. To account for a realistic dead line load, we will assume there are trusses oriented perpendicular to wall lines A and B, so half of the tributary area dead load of the roof will go to shear line A. The dead load of the roof is 0.6 kPa, so the width, which is 8 meters, divided by 2 times 0.6 kPa equals to a 2.4 kN per meter line load. Also, since we are adding a specific load, the software will factor the dead load contribution by 0.9 because it is helping the connector. So the code requires you to underestimate the amount of dead load. You can see the influence of both wind uplift and dead loads added to the structure, as well as the original 20 kN wind shear point load in this elevation view. Additionally, the effect of these loads on their respective hold downs are displayed at the bottom. So, while it was conservative to only add additional wind uplift, adding dead load can help counteract the effect of the wind. By including a dead load, in addition to the wind uplift load, the critical response of the hold downs has dropped by more than 20% compared to when we just added the wind uplift to the shear overturning. This difference could prove to be more significant in a bigger model. In fact, in this example, the combined hold down force is back below the design capacity of the hold down for almost all of the hold downs. One important note. The software acts similarly when designing a wall with an opening and when designing it with a non-shear wall. However, one difference is how the software handles dead loads. For non-shear wall segments, the software assumes the wall dead load is the same as the shear resisting walls and applies dead load right through the non-shear segment. But, if this was created as an opening, the software assumes there is no dead load over the opening. Therefore, different results are generated depending on whether the segment is a non-shear wall or an opening.